Welcome to W8.11 page 3. A few of you sent questions about this, maybe a little uncertain about how to run through this particular diagram here. Question number 7, so let's straighten that junk out right now. First off, if you notice, I'll color code, we have an incident ray labeled light. It is in air, incident on a boundary with material X. So if you notice here, this ray is our incident ray. There it is. Let's highlight this. Green for go. Go, light, go. There it is. There's your incident ray. It strikes the boundary. Wherever it strikes the boundary, fortunately here they drew the normal line, but if not, you would come over here, set yourself up perpendicular to the boundary, exactly where the incident ray meets the boundary, and dot somewhere along the 0, and at the 90, make yourself a nice dashed imaginary normal line that runs through the surface. Okay, now, every time you hit a boundary, 3 things happen. T, A, R. Oh, R. TAR. Transmit, absorb, reflect. And so, at this particular location right here, bam, TAR is happening. Let's get TAR. Now, there it is, purple. Popping purple. There's TAR. So, this green light will come here, it'll hit, some of it will transmit. We see that right here. Some of it will absorb. We will not see that in our diagram. Some of it will reflect. That is not drawn. So before anything else is shown here, we know for certain there's going to be a reflected ray at that top boundary which has not been drawn. Even though that's not part of this question, it's a nice review. Let's set this up. Notice that our angle is coming in at, don't read it, count. Let's see if we can count right here. Here we go. Alright, let's count. 10, 20, 30, 40, looks like 5. Looks like about a 45-degree angle right here. So this angle of incidence appears to be 45 degrees right here. Okay, well if that's the case, then you know that the angle of reflection will be also 45 degrees, except the reflection always happens on the other side of the normal, just as if you were playing pool. So it comes in, bounce, goes out. It goes out at 45 degrees. So let's count 10, 20, 30, 40, 5. Put a little dot up here at 45. And then finally, we can draw our arrow. Oh, and be true to you, what you're going to do is you're actually going to take your protractor, rotate, use it as a straight edge, and make sure that you're going through that point of intersection as well as your dot, which appears to be about here. And so then when you draw your line, nice and sharp, you don't actually have to hit the dot, you just have to go in the direction of the dot. There we go. Color code that one blue. And now we have our reflected ray off that top boundary. So actually, now you can actually see the incoming, the incident ray strikes. We have transmit. This one right down here to point P. There is your transmit. Let's make that red. So we have transmit, we have absorb, which you don't see, and we have reflect. Now, when this transmitted ray strikes point P, it has become the new incident ray. And so how will you possibly deal with this? Well, first and foremost, you got to go back to basics. This new incident ray strikes the boundary at point P, so you need a new normal line. The normal line is perpendicular to the surface, so come over here, get to just the right spot. Looks like right about there. And so you can mark for yourself. Put a little dot right here. a little dot right here, and we can connect those two with a dashed imaginary line called the normal line. And so let's draw that nice normal line right here. There we go. I'll shift it down ever so slightly. Perfect. Now, beauty of the normal line is it tells us where to measure. So where is the angle of incidence? It is not here. In fact, it is nowhere other than the angle between the new normal line and the incident ray that we care about for this particular part of the problem. That is, of course, this angle. That's the angle we care about. So, turn, check it out. Good. So the angle of incidence is, play the counting game, no need for subtraction or any other business like that. 10, 20, 30, 40, 50, 65. That's a 65-degree angle. Okay, so bring this down here, not 45, but 65 degrees. The angle of incidence now is 65 degrees. And like before, every time a wave hits a boundary, you will get tar, which means some of it will transmit, some of it will absorb, some of it will reflect. So, the easiest one to draw is the reflection, because the law of reflection says the angle of incidence matches the angle of reflection. So if it's 65 degrees, then it will be 10, 20, 30, 40, 50, 65 degrees this direction. So let us rotate. A little too extreme, maybe something like that. There we go. So draw your reflected ray. Now be careful. Your reflected ray starts from that exact point where the incident ray meets the boundary, and now it bounces in the direction of that 65-degree dot, but it doesn't go all the way to it. In this case, it only goes up to the new boundary. Then you'll have another tar. So let's come over here. This is the reflected ray, which we drew blue, so let's draw that blue. That also has a 65-degree angle. And actually, that's all this question asks for. Now, for those who are interested in the bonus, what you should notice here is we did tar. This green incident ray had both a transmit, there's the red, and a reflect. Now, this transmitted, which is also a refracted ray because it changed angle, this is now incident on a new boundary. And when it is, it will transmit, absorb, reflect. And so we drew the reflection. Absorption we don't draw. What about the transmission? Does it transmit? Now when you think of transmissions, you should think it should roughly head back out over here. Transmissions always roughly go in the direction they were going. So here this green incident ray up top roughly continued down and to the right, actually bent a bit. Now in material X you have this red ray, strikes a boundary, it will roughly continue off into this material. However, down and to the right. However, how does it bend? Does it bend? Well, let's see. You can actually do this with Snell's law. Works out just fine. If you figure out this angle up here, you could measure it. We'll call this a nice brute force method. At what angle did this refract? 10, 25. Well, that's not a surprise if you think about the angles. So we can actually figure out the index. So for the bonus now, we can actually figure out the index of refraction of material X. Then we could see about figuring out the actual refracted ray. So use Snell's law. You'll find the index of material X. And then using that, you can talk about the refraction back into air on the right side here by point P. See how it comes out. Okay, so that should be enough for this problem. But again, the key points are you have an incident ray, it hits a boundary, draw normal, and keep track of who transmits and who reflects. Now this becomes the new incident, hits a boundary, keep track of who transmits, well somewhere over here, who reflects. There it is. All right.